Okay, so today we are going to work on some mixed practice problems. I would like you to read through the problem, try it on your own. If you get stuck, start the video until you're good to go on your own, and then pause and keep going. Then use the video to check your answer. I would prefer if you don't just watch the video and write along with me. I want you to start using your own brain on these things. So with that being said, our first problem says when you weigh yourself on normal ground, your weight is 540 newtons. In an elevator, your apparent weight is 480 newtons. What are the direction and acceleration of the elevator's acceleration? So what are we trying to find? We're trying to find the elevator's acceleration and also the direction of that acceleration. So the first thing I'm going to do is draw two free body diagrams. I'm going to draw one for when I'm just standing on the ground and one for when I'm standing on the elevator, okay? When I'm standing on the ground, I have my weight, which we said is 540 newtons. And then I have some normal force that's balancing me out, right? When I'm on the ground, I have zero acceleration in the x direction. So the sum of all my forces in the x direction is zero. In this case, we know we don't have any forces acting on us from side to side. And then in the y direction, again, if I am not moving, there is no change in my velocity. If there is no change in my velocity, that means my acceleration is zero. If my acceleration is zero, my net force, or the sum of forces in the y direction, is going to equal zero, because force equals mass times acceleration. And no matter what our mass is, if our acceleration is zero, this whole term has to become zero. So if my net force is zero, that means that my weight and my normal force have to cancel each other out. So they have to be equal and opposite. So my normal force must also be 540 meters, or 540 newtons, sorry, in the upward direction, right? That normal force is pushing me up. You could have also drawn it where your weight is pushing you down and the normal force is pushing you up, okay? That would have also been an acceptable way to draw the free body diagram. So now, if we're in an elevator, now it says my weight, my apparent weight, is 480 newtons. With the elevator being our point of reference, are we accelerating inside the elevator? Are you moving in comparison to the elevator, right? And the answer is no, right? If the elevator is our frame of reference, all we're doing is standing there. The elevator itself is moving, but when we use that moving thing as our frame of reference, we're not moving. Similarly to when you're sitting in a car, right? The car is moving, but if you're using the car itself as your frame of reference, you are not moving. Hopefully you remember us talking about that. So with the elevator as our frame of reference, if this is you, we again would have some normal force that is equal and opposite 480 newtons. Hopefully you remember us talking about apparent weight from the other week. And I'm going to pull this out. There are ways that we can solve it without the apparent weight formula. You could solve it just based on what you already know. Sorry, I should have gotten my textbook out before. So we could say that the difference between these two weights, whether our weight on the ground and our actual weight, is going to be the sum of our forces in the y direction. Because we know that the elevator is going to be pushing us presumably up, right? If we get a negative number, that would mean that it's pushing us down. But the elevator is pushing us with some sort of force. And so we must be doing some sort of acceleration. And we have some sort of mass attached to that as well. So we have our weight of 540 newtons. And then we have this additional force. So when we have our real weight of 540 newtons, we have some sort of additional force. And that is going to cause our weight to change, right? So if we're thinking about the whole thing, this is me. And when I'm in the elevator, like my weight towards the earth is still going to be the same of 540 newtons. But then I'm going to have some sort of force pushing me off or pushing off of me to offset that. So we know that the total offset of this is going to be 480 newtons. So now we have to find this force. Well, the difference between these two forces is going to be 480 and 540, the difference between them. So when I get out my calculator, 540 minus 480, it's going to be 60. And we know that 60 has to be in the opposite direction of our 540 because it's actually going to be a negative 60, which tells me that it's in the opposite direction of that 540. So we have 60 newtons, and we know it's acting upwards, right? Because our weight is pulling us downwards, and that force is counteracting it by 60 newtons. We also know that force is equal to mass times acceleration. Well, we don't know our mass, but can we find our mass? Yeah, we can find our mass making assumptions because we know that weight is equal to mass times gravity. We're going to assume that gravity is 9.81. So I know that my weight equals my mass times 9.81. And I know that my weight on the ground is 540 newtons. So now I can take 540 divided by 9.81. And it's 55 kilograms. So now I can plug that 55 in. So I have 60 newtons equals 55 kilograms times my acceleration. I can then divide both sides by 50, excuse me. I can divide both sides by 55 kilograms. And when I divide 60 divided by 55, I get 1.09. And to make this fit my sig figs, I'm going to do 1.1. Units for acceleration are going to be meters per second squared, right? Is my acceleration. And then we said, hey, if we're counteracting is 540 newtons upwards, I have to be accelerating in the same direction as my net force, right? That's Newton's second law. Force equals mass times acceleration. Force is always in the same, net force is always in the same direction as acceleration. So I have to be accelerating at 1.1 meters per second squared upwards. All right, next question. A 22 kilogram chimpanzee hangs from the end of a branch. The branch sags downward through a vertical distance of 13 centimeters. Treating the branch as a spring, satisfying Hooke's law, what is the spring constant? So if I wanted to, I could draw this out where I have the branch and I have the chimpanzee hanging from it. Okay, looks like a person, it's a chimp. I was going to draw a tail, but chimps don't have tails. So this distance right here is 13 centimeters. The very first thing I see is centimeters, but we know that centimeters is not our standard unit. So the first thing in my brain that I know I need to do is change that centimeters to meters. There are 100 centimeters in a meter, so I need to move the decimal point over 2 spots. So this is equal to 0.13 meters. That's the very first thing I'm going to do. Now I look at this problem and I'm going to say, well, what is it actually asking me to find? It's asking me to find the spring constant. And it says I need to use Hooke's law. Well, what is Hooke's law? Hooke's law is that my force is equal to my spring constant K times my displacement, or my change in length, X. Well, now we have to think, okay, well, what are the forces acting on this branch? I have a weight pulling on this branch, right? This branch isn't going to have a normal force, right? The branch doesn't have anything that's pushing it up. It just has a weight that's pulling it down. And we know that weight is equal to mass times gravity. And we know that the mass is 22 kilograms. And we know that gravity is 9.81 meters per second squared. So my total force, I'm going to plug this into my calculator. 22 times 9.81 is going to be equal to 215.82 newtons. But looking at my problem, 2 sig figs. I'm going to keep all of this for now, but I know I'm going to change my final answer to be 2 sig figs. So my force is going to be 215.82 equals K, some spring constant, and we know we're not going to have that because it's what we're solving for. And then X is my displacement. Hey, we know that. 0.13 meters. So when I do that, 215.82 divided by 0.13, this is the number that I get approximately. But I said, hey, I want to change this to 2 sig figs. So I'm going to keep these first 2 digits. I'm going to round the first 2 digits and then make everything after it a 0. It's going to be 1,700 Our units are going to be newtons per meter is my spring constant. The spring constant essentially says for every meter that I displace this spring, it's going to take 1,700 newtons of force. That's just another way of thinking of that spring constant. So this one is a pretty strong spring, but if you think about it, it's a tree branch. So that would make sense. All right, moving on to the next problem. In a helicopter rescue, 2 men with combined mass of 172 kilograms are lifted to safety. Determine the tension in the cable if the men are lifted with a constant acceleration of 1.1 meters per second squared. All right, so I'm going to start with a free body diagram. This dot is going to represent my 2 men. What kind of forces are acting on these 2 men? I have the weight of the 2 men equals mass times gravity is equal to 172 kilograms times 9.81 meters per second squared. And when I do that of 172 times 9.81, I get 1,687.3 newtons. Okay. Well, what other forces are acting on these 2 men? I have a cable that's pulling them up with a tension, T. My T is not going to equal my W. Why? Because this thing is moving, right? The men are moving. If the men are moving upward, right, they're getting pulled towards the helicopter, they're going to have some sort of acceleration. If they have an acceleration, the sum of all of my forces is not going to equal 0. I know that the sum of forces in my x direction is going to equal 0 because I don't have any sort of forces pushing them this way, and they're not accelerating to the side. They're accelerating upwards towards the helicopter. But I know the sum of forces in my y direction is going to equal mass times acceleration. Do we know the mass? We do, 172 kilograms. Do we know their acceleration? We do, 1.1 meters per second upwards, so it's just going to be a positive 1.1. So when I take 172 times 1.1, I get a net force in the y direction, or the sum of all of my forces in the y direction, is 189.2 newtons. We also know that the sum of forces in my y direction is going to be my tension in the rope holding me up minus my weight, right? When I look at this, my tension is positive, my weight is negative. These are the only 2 forces that I'm going to have, so I add them together. Positive T plus negative W ends up being T minus W. So now I can take these 2 things and set them equal to each other because they're both equal to the sum of forces in my y direction. So now I can say 189.2 newtons equals T minus W. I'm going to rewrite this now because we know W and we're looking for T. Now I have to look at this and say, okay, how do I get T all by itself? Well, I'm subtracting, so now I need to add 1687.3 to both sides. So that cancels out on this side. $189.2 plus 1687.3, 1876.5 newtons is equal to T. But then if we look at sig figs, we have a 1.1, we have a 172. So the 172 has 3 sig figs, this has 2 sig figs. We always go to the least number of sig figs in our problem. So this gets changed to 1900 newtons is my tension. Or you could leave it like this, but scientifically speaking, sig figs, we would go to this one. All right. I think we have 3 more problems. So 2 workers pull a net through a pole to clean it as shown below. One worker pulls 130 newtons at 34 degrees relative to the net's forward motion. That's this guy, 130 newtons. And we have 35 degrees here. The other worker pulls at an angle of 45 degrees. How much force should this worker, they, use to ensure the net moves straight forward? Again, I'm going to start with a free body diagram. So I'm going to change this a little bit. And I'm going to draw a dotted line in just to act as my reference. So I have 35 degrees, 130 newtons. And we have 45 degrees and some sort of force. So if we're thinking about this from a graphical approach, in order for us to get some sort of force or some sort of movement that is purely horizontal in this direction, the forces in the y direction need to be equal and opposite. Can we tell right now how much of this force here is in the y direction and how much of this force here is in the x and y direction? We can't. So what we need to do is split these forces up into their x and y components. How do we do that? Hopefully you remember that we're going to have to do a little bit of trigonometry. We're going to have to do a little bit of SOHCAHTOA. So if I want my y direction, that's going to be this way. And it's going to be this way. Looking at the triangles here and looking at where my angles are at, I know that this is going to be opposite. So I'm going to have sine theta equals opposite over hypotenuse. And sine of theta equals opposite over hypotenuse. So sine of 45 equals opposite over F. We don't know how much we need that to be yet, right? We don't know what our force F is. But down here, we have sine of 35 equals opposite over 130 newtons. So now we can figure out what that opposite is. We're going to end up taking sine of 35, which is 0.573, times 130. So this gives me my opposite is 74.56 newtons. So I know now if I'm going to redraw my free body diagram and splitting this into x's and y's, I've got 74.56 newtons in this y direction. So now I know that my opposite here right here, this opposite, right, this right here, we also want to equal 74.5 newtons to balance out our forces in the y direction, so that way we don't have any sort of acceleration in either of these directions, right? Because if our net force is 0, we're not accelerating in that direction. And then we can leave all of the acceleration for this direction. So I'm going to move this. I'm going to start over here. So sine of 45 degrees equals 74.56 newtons over my force. Now I have to rearrange this to get force all by itself. To do that, I might say force times sine 45 equals 74.56 newtons, and then say force equals 74.56 newtons divided by sine of 45. So then I do 74.56 divided by sine 45. My force is equal to 105.44 newtons. Which I'm going to round to the nearest newton and say that my force is 105 newtons. That's it. We don't have to further split this up into the x components because we're not asking us to find then what is our, we would need to do that if we were trying to find like what is our acceleration then in the straightforward direction, because then we would have to find the sum of our forces and multiply by the mass of the net. But we don't have to do that because we were simply trying to find what is the magnitude of this force. And we've done that, right? We found F. Okay, 2 more questions. You push a box along the floor with a constant force of friction. When you push with a horizontal force of 75 newtons, the box's acceleration is 0.5 meters per second squared. When you increase the force to 81 newtons, the acceleration is 0.75 meters per second squared. Find both the mass of the box and the coefficient of kinetic friction between the box and the floor. All right. So now let's think about kinetic friction. We know that the force of kinetic friction is equal to the coefficient of kinetic friction times our normal force. We also know that force equals mass times acceleration. Or a net force, right? Well, we know here we could find the box's mass by using either one of these, right? We have a matching force to an acceleration and a matching force to an acceleration. We can even use that to double check our mass. So I might say that 75 newtons in the y direction, or sorry, in the x direction. This time we're talking about sliding, right? So this would be sum of forces in the x direction equals mass times 0.5 meters per second squared. So my mass is 150 kilograms. And now I'm going to check this by saying 0.75 times 150. Ooh, 112.5. So there must be something that I'm not thinking through. What could I not be thinking through? Well, let's draw a free body diagram. I have my box. I'm going to have some sort of weight. I'm going to have some sort of normal force. And then I'm going to have some sort of force that I'm pushing the box with, and some sort of opposing kinetic friction. Sorry, I'm looking to see if this is a problem in the book, so that way I can make sure that I copied it down right. I believe it is, so give me just a moment here. So we could also say, we could also rewrite this, right? We could say the force of kinetic friction is equal to the coefficient of kinetic friction times our normal force is going to equal mass times gravity. We know for both of these, our normal force, or sorry, our force of friction, or our kinetic friction, is going to stay the same because our normal force is going to stay the same because our mass of the box is not changing, right? So the sum of forces in my x direction, it's not just as simple as mass times acceleration, right? Because it's going to be some force of mass times acceleration, which is my F here, minus my mu sub k m times g. I'm getting stuck on this one, and I don't think I should be. Let's see. We could also maybe rearrange this to know that my mu sub k is going to be equal to my friction divided by my normal force. Or I could rewrite this as my friction divided by mg. My kinetic friction, or my, here we go, here's what we're going with. So then I could also rewrite this as my kinetic friction force is going to be equal to my mass times my acceleration divided by my mass times gravity. Now I get my coefficient of kinetic friction is equal to acceleration divided by gravity. So for both of these, we're going to have a different coefficient. No, we're going to have the same coefficient of static friction, right? Yeah. So that's not right either. All right, we're going to skip this one and come back to it, because right now my brain is not working super well. So you decide to go on a hot air balloon ride with friends. With only one person left aboard, the balloon is neutrally buoyant with a total mass of 1,220 kilograms. After the last person boards, it accelerates downward at 0.56 meters per second squared. What was that last person's mass? So force equals mass times acceleration, or the sum of forces in my y direction, my total force. If I'm thinking about my hot air balloon, I'm going to draw before they board and after they board. So before they board, I've got a mass of 1,220 kilograms, which translates into a weight of mass times gravity, which is 1,220 times 9.81. So I have a downward weight of 11,968.2. And we said it's neutrally buoyant, so it's not going anywhere, which means that the sum of forces in all directions is equal to 0. So I must have an equal and opposite 11,968.2 newtons. And then one more person gets on. So I still have an upward force of 11,968.2 newtons. And I still have this downward force of everybody in the balloon of 11,968.2 newtons. But then I also have this added weight of the person, which is equal to their mass times gravity. So the sum of all of my forces in the y direction is equal to mass times acceleration, the total mass times acceleration, which is going to equal 1,220. Here, actually, but the sum of all of my forces in the y direction, we also know, is going to be a negative mass times gravity. Mass of the person. This would be total mass times acceleration. So our total mass is going to be 1,220 plus, mass of the person times a negative acceleration of 0.56 meters per second squared equals negative mass of the person times 9.81. So now we have to sort out all of this and get mass of the person all on one side of the equation. So I'm going to distribute, first of all, I'm going to distribute this negative 0.56. So I have negative 683.2 plus minus, plus a negative, right? So it's going to be minus 0.56 mass of the person equals minus mass of the person times 9.81. Now I'm going to divide both sides by 9.81. And actually what I'm going to do first is I'm going to multiply everything by -1. So I'm going to make this positive, positive, positive. Because everything, all of our terms right now are negative, so I can multiply everything by a -1 to make it all positive, right? So now I'm going to divide both sides by 9.81. That 9.81 has to be distributed across both of these terms because we're adding. So I'm going to do 683.2 divided by 9.81. It's going to be 69.64 plus, and then I'm going to do 0.56 divided by 9.81. .057 MP equals M mass of the person. So now I can subtract this 0.057 MP. So I'm going to have 69.64 equals, we're going to do 1 minus 0.057, 9 or 0.943 mass of the person. The last thing I need to do is divide both sides by 0.943. So 69.64 divided by 0.943 is 73.8 kilograms. That's a reasonable size for a person, right? That's going to be right around 160 pounds. Let's just check our answer here. First, I've got to figure out what question it is. Yep, and that is right. So 73.8, or we could round this to 74 kilograms. That is our last practice problem. Try this one on your own, see if you can figure it out. If you can, go ahead and help the other people in your class. And then if we can get it figured out, maybe I'll post another video.